From military reconnaissance to epic video shots, drones have truly revolutionized our world. Shown here is footage from the DJI Mavic Pro, which retails at about $1,000 and is used by professional videographers all over the world. But for the purposes of this video, we will not be looking at this. No, we'll be looking at this. This is the Bangcool Mini RC drone, which you can buy for about $12 from China. Batteries not included. Luckily for us, the dynamics and controls of all quadcopters are very similar.
To start off, a quick overview of how quadcopters work will be given. The dynamic system is what relates the inputs to the outputs. So for the case of a quadcopter, this would be the electronic motors attached to each rotor. Important features of these are generated torque and thrust. This system is going to be continuous, otherwise the quadcopter would essentially act as a headless chicken flying uncontrollably. The inputs to the system are going to come from both the user through the remote control and the onboard flight controller adjusting itself during flight. The outputs to the system are going to be changes in thrust that each motor produces. This is what allows for different kinds of motion. The onboard inertial measurement unit measures accelerations through the accelerometer, and the gyroscope measures angular velocities. These allow the quadcopter to determine its orientation. The flight controller is a proportional integral derivative controller that maintains stability by correcting the error between the user input and its orientation. The flight controller is constantly measuring data during flight. As mentioned previously, these are angular velocities, accelerations, and the calculated Euler angles.
Shit, that was good.
Right. Here is an overview of the inner workings of this quadcopter. The radio signals from the remote control get transmitted to the flight controller via the antenna. The flight controller then feeds the information to the electronic speed controller located beneath the props. The ESC controls motor by varying the amount of voltage supply using pulse width modulations. This creates the desired motor outputs that the user inputted. The governing equations of motion are seen here. Linear motion is achieved through Newton's classic force equals mass times acceleration equation. Angular accelerations are achieved through a non-zero net torque on the system through different combinations of motor output. In general, both of these equations will be at play when flying the quadcopter. This is an overview of the remote control and how it affects the motor outputs. Notice how opposite diagonal motors spin in the same direction. Drones are designed like this so they wouldn't be constantly spinning. Because of angular momentum is conserved, by increasing the speed of opposite motors, the quadcopter will yaw while maintaining the same amount of lift to compensate for the angular momentum caused by the motors. Another example seen in this video is a flip, which is essentially a roll movement.
The two frames involved in quadcopter dynamics are the inertial pilot's frame and the non-inertial quadcopter body frame. Calibrating the quadcopter to a flat surface before flying sets the Euler angles to 0 and ensures somewhat stable flight. As seen in this flight demonstration, the user inputs rotate the body frame axis, but Euler angles are always relative to the pilot inertial frame. The flight controller measures these to determine its orientation and how much thrust it needs. To summarize what we've learned, here's a basic block diagram simplifying the system down. Radio signals from the remote control are received by the antenna on the flight controller. Signals from the flight controller are then sent to the electronic speed controller to vary the motor speed using PMWs. Variations in motor speed are what causes linear and angular accelerations that allow the quadcopter to yaw, pitch, roll, increase, and decrease altitude. All the while, the inertial measurement unit measures accelerations and velocities to determine angular position with Euler angles. To achieve what the user inputted, the PID controller algorithm measures the instantaneous error, integrates the past errors, and differentiates the errors over time. The flight controller makes adjustments based on this to reduce the error and sends those to the ESC and to the motor to continue the control loop.